3.3, question number 1. So this section is not due next time, but it'll be due time after. Like, we're going to start it now. We'll finish it on Monday, and it'll be due on Wednesdays. That makes sense. We've got a week for this one. It's going to be a hard section. We want to do half today, the other half on Monday. Take our time, because it's probably one of the hardest sections of the course. So, a probability, conditional and expected value. So let's start off with giving a test to a group of students, the grades and gender, blah, blah, blah. One student is chosen at random, find the probability. Well, this isn't new. This is the same stuff, this first question, huh? Male, yeah, I'm going to skip that. You guys know how to do that, right? That's just kind of review of the same stuff. Well, maybe I'll do one of them. What's the chance they were male? So if we grab one person at random, what's the chance they're male? Total's on the bottom. 68. Male goes on the top. How many males? 27. Hit the buttons on your calculator. Do they want decimals, or what do they want?
Fraction.
Where does it say that? Oh, when you click the box, you see? Yeah, good. So now if you want to do that fraction, remember, just put it in your calculator. Math, enter. Just go math, hit the math button. I don't think it's reducible. It's not. It won't. Nothing will happen. That's it. But if it was reducible, the calculator would reduce it. So when you have this in your calculator and you get a decimal, then hit math, enter. It'll change it. It'll end up being the same. It'll stay 27/68 because that one's actually not reducible. Nothing divides into 27 and 68, right? So it stays that way. Yeah, so we good with these? These are all just fractions. Just hit math, enter. Oh, no, let's jump down to D, though. D is different. Yeah, let's do D. Yeah, D says if one student is chosen at random, find the probability the student was male given they got an A. Yeah, so it's the probability that they're male given they got an A. So how do we do that? Remember what given does. Think about what I was saying with the dice. If I roll a die and I say, what's the chance I got a 6? Be 1 in 6. But then I give you more information, like insider trading. I say, hey, I got a number higher than 4. Then that changes it, doesn't it? Now you know it's either a 5 or a 6. That changes the probabilities. Probabilities are just a matter of knowledge. That's all they are. So when they give us information, that changes the denominator. That's what changes. Everybody see that? It changes the total possibilities. It changes the denominator. So we're given that it's the person got an A. So we grabbed a student at random. We're saying, hey, what's the chance it's a male that we grabbed? Let me give you some information. I did get somebody that got an A. So I picked a name at random on the roll, and I say, hey, what's the chance I got a male? By the way, I did get a person who got an A. That's what they're saying. We're given they got an A. So the bottom, the total, is not 68. It's not all people that are possible now. Now we know it was a person who got an A. So what's the bottom? Yeah. How many people got A's? 22 people. It has to be one of those 22, doesn't it? Has to be one of those people who got an A. There's 22 people. 3 males, 19 females who got an A. It has to be one of those 22, not any of the 68, huh? See how it changes the denominator? That's what this section is all about. That's called conditional. We're giving a condition. We're saying it's not just anybody, it's somebody that got an A. That's a condition. Just like when I roll the die and say, I did get a number bigger than 4. That's a condition. That's conditional probability. So it changes the denominator. What goes in the top then? Yeah, how many males? 3 out of 22. How we doing? Is that making sense? Conditional probability. Given something.
What about letter C?
Find the probability it was male or got an A?
Yeah.
Yeah, so those are like the other ones we did. Right? So you would just do male or A over the total. So the total is the whole 68, because there's nothing given on part C. Does that make sense? So if there's nothing given, then everything's a possibility. Just like if I rolled the die and didn't say anything, then all 6. And male or got an A. How many people are male or got an A? Yeah, 27 males total, right? You could just add these 3 up if you want. It's 27. Or got an A? Plus the 19. So that's just like the other ones we did, right? 27 plus 19 over 68. Whatever that comes out to be. All right. Okay, here we have a different question. So list 64 speeding tickets on I-25 in Colorado. So 8, what is it? So 8, well, tell me about those males. Yeah, they got a ticket for speeding. They were 0 to 10 miles an hour over the limit. What about that 4? What's that mean? Females who barely got a speeding ticket, basically, right? How about these 19? Yeah, 19, they were males who went 10 to 20 over the speed limit. 10, those are females who did that. What about these 17? Really fast males. Yeah, more than 20 over. And the 6 females, same thing. All right, so with that in mind, the table's making sense. Let's go for the questions. If a random ticket was selected, what would be the probability the driver was female? So we'll just start with that. If you just grab somebody at random, what's the probability that it's a female? Yeah, so that's nothing given here, right? They're not giving any conditions, so they're not limiting the field in any way. It's the whole 64. And how many are females? 20. 20 females out of 64 total people. This one wants decimals, no fractions. Just hit the buttons when you calculate. Now B, let's go on to B. Given, they're starting in with a given right away on B. Given that a particular ticket had a male offender. So they're limiting the possibilities, aren't they? They're saying it's a male. What's the chance it was more than 20 over? So if you know it was a male, what's the chance it was 20 over? More than 20 over? So the bottom is going to be, we've got a lot of room there. Bottom is going to be the total. What's the new total? The total becomes more limited, huh? It's not any person that's possible. What's the denominator going to be? The males, huh? The bottom is going to be the males. That's the, I should just do it that way. That's the total we're looking for, is the males. So how many males total? 44. 44 males. And how many of those males were more than 20 over? 17. 17 out of 44. Then just divide and get a decimal. Is that making sense? On the condition, limiting the denominator there. Right? They're saying they were given that it was a male. So that means it was out of the 44 males, 17 out of 44. All right, how about part C? Given that a particular ticket was 10 to 20 miles an hour over the speed limit, what's the chance it was a female? Can you do that one real quick? All right, so given that a particular ticket was 10 to 20 over the limit. So that's our denominator, isn't it? 10 to 20 over. So how many is that? 29. That's the total tickets that were 10 to 20 over. 29 is that denominator. Is that good? And what's the numerator? Probability the driver was female. Out of those 29 people who got a ticket for 10 to 20 over, how many are female? 10. Is it making sense? 10 out of 29. Are we good there? 10 out of 29? And then just hit the buttons on your calculator. Questions I can answer on that one? The rest on this one seem kind of the same. Well, we could do, I don't know. Why don't we jump down and do... I think F is the hardest. How about we, let me go fresh screen here. The other parts are easy for you. Let's do F. Can you read F? F says, here's part F. I'll just do F right here. Probability female or 0 to 10 miles per hour over. That's what they're basically asking. No given at all. Nothing given at all. Just, out of there's no given. No given on part F. It's just saying, hey, if you just grab somebody at random out of the whole group, what's the chance they're either a female or 0 to 10 miles an hour over? So sometimes that could be tricky though. So or we're going to add up those categories, right? The denominator is going to be, what's the denominator? Yeah, the whole total. Because, again, there's no given, so we're not limiting anything. No insider trading here. No given information. So how many are female? So it'd be these people, these people. Those are all the females, which totals 20. Who else do we need to include?
The male,
That 8 right there, huh? Because they're in the 0 to 10 miles an hour over the limit category. Is that making sense? We good? These getting easy? You can do these in your sleep now. That's my hope. They're getting that easy. Kind of the same thing every time, huh? Good? All right, so, and let me know if you're looking at the homework and there's particular ones you want to see, let me know. I do take requests. All right, what is the probability that someone, so we have this big table. I'm going to skip the first question, second question. No, second one would be good. Let's do the second one. What's the probability that someone has at least 2 children? Let's make sure the data table's making sense first off. Tell me about those 11 people. What do you know about those 11 people? They're from the U.S. and they have no children. And what about these 12 people? From outside the U.S., again, no children. How about these 20 people? Single child, outside the U.S., etc. Is that good? That table making sense? All right. So if you grab somebody random, what's the probability that someone has at least 2 children? Is there a given on this question? Not this part anyway. There's not even a given until further down the line. So this has no given, so that means the denominator must be the 87, huh? But what's the numerator?
17.
Be careful. I think you might not be giving that word his meaning. Yeah, at least 2 children. If I said my family has at least 2 children, that doesn't mean 2. That means 2 or more, huh? So 2. So we want this and this. It's 2 or the 3 or more category, huh? Everybody seeing that? At least 2. So that would mean we'd add the 17 and the 22 to be, what is that, 39 out of 87. Hit the buttons on your calculator. Good there? All right. Let's jump down. Let's jump down to the given. I think the rest will be straight for you. Given that a person is from the U.S., what's the probability they have 3 or more children? Given that they're from the U.S., what's the probability they have 3 or more children? Yeah, so the given is going to limit things, huh? So whenever they give us a given, that's going to narrow the field. We're not talking about every kind of person now. We are given the information that it's somebody from the United States. So the denominator is from the U.S. now. It's not the overall total. It's just the total people from the U.S., huh? Because that's what we're given. we're given that they're from the U.S. So how many are from the U.S.? Yeah, 43. Getting used to all these tables? We're getting easier? Right? From the U.S., 43 total. And what do they want? 3 or more children? What's that going to be? Just the 8. Right? 8 of the 43. How are we doing? Is that good? Does everybody see that? There's 43 total people from the U.S. and 8 of them have 3 or more children. Why don't I use the 8 and the 14 or total them up to be the 22 on the top? Those are all 3 or more. Shouldn't I put all those on the top? No, why not? Yeah, they said we're only talking about people from the U.S. That's given, right? So that means we're not talking about the 14 or the 22 because that's from outside the U.S. And that's the total of both, just the 8. Good? All right, how about the last one? Given that a person has 1 child, that's supposed to be a W there, what is the probability that person is from the U.S.? So try that one. So given they have 1 child, so take that given, that's your denominator, right? Given that they have 1 child.
So would it be 16?
Yeah, so what's the denominator? What's the 1 child?
Oh, yours. I'm sorry, I said mine.
25 is the 1 child denominator, right? Because that's the total number of people that have 1 child. And then the numerator is, what do they want? From the U.S. So how many of those are from the U.S.? 20. Of the 25 people that have 1 child, 20 of them are from the U.S. So the probability, if you grabbed a person that has 1 child, the chance that they're from the U.S. is 20 out of 25. Because 20 out of those 25 people, of those 1 child people, are from the U.S. So there we go. Divide that in your calculator. You'll get 0.8, I think. They want decimals on this one? Yeah, decimal on that one. That good? Easy enough? Not too bad? Okay. So this data, let's make sure we understand the table first off. Tell me about those 38.
They think the market is better.
Yeah.
And they're Republican.
Yeah. They think the market is getting better, and they're Republicans. Right? With the markets, yeah, U.S. economy. The U.S. economy is getting better, and they're affiliated with the Republican Party. How about these 12 people? They think the economy is getting better, and they're Democrats. And these 21 people, they think the economy is getting better, and they're not affiliated with either party, right? And then, like the 104 there, they think, what do they think? Economy is about the same as it was, and they affiliate with the Republican Party. And then, like, how about, what's that 137 there? They think the economy is getting worse, and they're Democrats. Okay, so with that information, and we have the total, 651. Okay, so what's the chance they're Republican? If we just grab somebody random, nothing given here, right? There's no given right there. So what's the chance they're Republican? Well, the bottom's going to be the total, which is the 651. So how many Republicans? Oh, they didn't give me totals, did they? I got to just add those up. I got to add all those up, don't I? So whatever, 38 plus 104 plus 44, and just whatever the calculator says. Good there? Good so far? Part B is not a problem. Let's jump down to part C, this third one. I haven't explained that straight line that's between them. Let me write that for you. So the probability better, and then they have this straight line. I'll make it bigger. The straight line right here, and then Republican. Okay, you know what that straight line means? Given. That's the shortcut symbol for given. That's a shorthand symbol for given. So when they do that straight line like that, that's what statisticians use that for the word given. That's a shorthand symbol for given. They use it so often, they actually have a symbol for it. So they're saying to us, that means, what is the probability that the person is better? Well, they're not better. They think the economy's better, given they are a Republican. They affiliate with the Republican Party. So what's the problem? What's the probability that they think the economy's getting better, given that they're a Republican? So that thing that comes after the line is what you're given. That's going to limit the field, isn't it? So the denominator is going to be Republicans, isn't it? Because that's what we're given. We're given that we're talking about a Republican here. Right? That's what's given. So how many Republicans are there? Is that what it is? This total here? These right here, they add up to 168?
186.
186? Is that what it is? 186? 142, 82. Yeah, 186. Yeah, so 186 is the total. So we're talking about one of those 186 people, aren't we? That's the total Republicans. So what's the chance they think the economy's getting better, given that they are Republicans? So we know we're talking about a Republican, somebody out of the Republican group. What's the chance that they believe, they feel, the economy's getting better? 38. Then just divide it on your calculator. How are we doing? Is that making sense? So again, whenever you're given something, that becomes the denominator, doesn't it? Because you know that's your possible pool now. You're given, it's Republicans. We're only talking about the 186 Republicans. Out of them, how many think it's better? Let's try the reverse now. Notice how they're switching it here. Republican and better. They're swapping it. Can you do that one? What's the chance they're Republican given they think the economy's doing better? That's a different question. The order matters, you'll see. So try that one. Let me give you a second. Try that one. So on that one, what's the denominator going to be? Which one's the denominator? The Republican or better? The better, because that's what you're given now. Now they're saying, we're talking to somebody who thinks the economy's getting better. We may or may not be talking to Republican. But for sure, we're talking to somebody who thinks the economy's getting better. That's what you're given. That's what you know for sure. So what's the probability that they're a Republican given they think the economy's getting better? Given they think, I'm kind of running out of room. I'm going to go to a fresh screen here. So let me bring this one up here. So what they're saying is the probability that they're Republican, given they think the economy's getting better. So we're given the better. We know they're a person who thinks the economy's getting better. So whatever comes second, that's what you're given. That's what you know. That's what limits the pool. That's going to be the denominator, huh? The better is now the denominator. So how many think the economy's getting better? Whatever those add up to be, huh? What is it? Is that what it is? 50, yeah, 71. Good. 71. It's one of those 71 people, huh? It's got to be one of those 71 people we're talking about, because those are the only people that think the economy is getting better. Those 71 people. So out of those 71 people, how many are Republicans? 38. So it's Republican out of better. Now that answer is different than the last answer. Notice that. So you see how the order matters? The probability of better given Republican is different than the probability of Republican given better. Those are different questions, aren't they? Those are definitely different questions. I'm interested to share with you next week on Monday. I think I'll do it next. I think we'll read next Monday. I'll show you when we finish up the given stuff and you're more comfortable with it. I might wait till Wednesday till you're really comfortable. But I want to show you one of the most famous statistical blunders that people make. And it's about this given. If they think you can switch the order, even they being doctors. There's a question that 95% of doctors get confused on because they're not careful about which way the given goes. I'll show you. It's famously known. And it's a given question, and they're reversing the given. And it just sounds that way. Something about cancer. If you test positive for cancer, what's the likelihood you really have cancer? Doctors, 95% of doctors, when they're asked this question, confuse it with the other way. So you'll know more than 95% of doctors if you get this given thing straight. Conditional probability is a little confusing. I'll show you the example next time. It's all about testing positive for cancer versus the chance of a false positive. So that's a little different, and we'll work it out next time. But so this is something that people deal with in the real world. If you test positive for cancer, what's the chance you've really got it? Versus the other question, same kind of thing here. Now let's answer the last one. I think that'd be a good one. What's the probability that you grab somebody random that they're Republican and they think the economy's getting better? On that last one, is there a given? Is anything given on this one? No. Nothing's given, so we know the denominator is everybody. Oh, I don't even know what. 651, huh? There it is. So the denominator is 651 because it's out of everybody. We're not limiting the pool with any given. And so what goes in the top? Yeah, good. You get snapping these out now. Piece of cake for you. That's right. It's just the 38, isn't it? Because those are the only people that are both Republican and think the economy's getting better. So there it is. That good? Making good sense? All right. So number 8, very important question. In a large school, it was found that 72% of the students are taking a math class, 77% of the students are taking an English class, and 52% of the students are taking both. Find the probability that a randomly selected student is taking a math class or an English class. What do you think about that? Exactly. Yeah, this is the kind where you need to make the table. They don't say it anywhere, do they? So we need to make a table. Yeah, so make a note of it. 8 and then 9 is going to be the same thing. We need to make a table. There'll definitely be one like this on the exam. No secrets with me. Exam number 2, I will for sure give you. There'll be one in the practice exam, so you'll have practice with it. And for sure there'll be one in exam number 2 where you've got to make your own table. I think it's a very valuable thing because that's how information comes at us, just straight. Not always in a table, huh? So we got to make our own table here. Now, when I say make our own table, like what kind of table? Well, kind of just like the other tables. What do I mean? Let's look back at some. Well, that was a weirder table. Let's look back at. Well, that was a weird one too. They were all okay. Yeah, there's a more normal one, like that, right? Like where you have the various grades at the top, and then So one of the conditions on one at the top, like that'd be grade, huh? And on the other side, gender. So basically, you put one quality on the top and one quality on the side. In this case, grade and gender, or in this one, it's again genders on the side here. Oops, I lost that one. Where am I at? Genders on the side and speed. How fast over the speed limit was there? So, getting back to this one, I'm going to put. It doesn't matter which way you do it. I'm going to do. Did they take a math class on the top? I don't really have room here. I need to get some more room. Let me move it over. So this is number 8. And 72% are in math. 70% take math. And what percent? 77 English. 77% take English. And 52% both. Take both. Okay, so let's make a table, and it's going to be math on the top, English on the side. You could do it the other way. It doesn't matter. Like that. And I'm going to put, yes, they're taking math. No, they're not. And over here, English. Yes, they're taking English. No, they're not. So, again, when you make these tables, you put one characteristic on the top, one characteristic on the side. So grades and gender, English and math, Republican and what they think of the, or party affiliation and what they think of the economy. So one characteristic on the top, one on the side. Doesn't matter which way you do it. And then you start filling in the information. So do you remember how this works? So 72% take math. Good, yeah. That's the total, isn't it? That goes down here. That's the total amount that are yes to math. It's not. It can't go in any of those individual boxes because it's the total that are taking math. Yeah, remember that? We did one. I think we did one of these in the last section, huh? Just one. And then 77% are taking English. Where's that go? Yeah, it's over here. It's the total. You can write total if that helps. Probably a good idea. Total. It's the total that are yes to English, huh? Yeah. So 77% taking English, 72% taking math, 52% take both. Where does that go? In the yes, huh? Right there. My fives always look funny. 52% right there. Good? Because they're yes and yes, right? They're taking English and math. Both. And now can we get the rest of the table? How do we know what goes here, for example? Yeah. Does that make sense, right? Because 72% total are taking math, 52% of those also take English, so that must mean subtract, right? So 20% are yes to math, no to English. They're in a math class, but they're not in English class. And then this number, subtraction again, huh? Right, everybody seeing that? It's going to be 77 minus 52. What's that? 25%. Here, let me show what I did on this one too. I just did the 72 minus 52. Got the 20. We good there. Now, how am I going to get like that right there? Got to add it to 100, doesn't it? Yeah, we got to have 100% all the other in that box. So, so we got 52, 25, and 20 right now. What's that? 97. So it only leaves 3%. 3%. So now we're ready. All that's just the build-up, the get ready to answer the questions. So now we're ready to answer the questions. All right, so what are the questions? Find the probability that a random selected student is taking a math class or an English. So, let me write that out here. So, probability. So, this is like part A, which is first one. Probability that they're in math or English. So what's math or English? 97%. Yeah, you good with the or? It would mean all three of these categories, huh? All three of those boxes, I should say. It's going to be all three of those boxes because these boxes, they're people taking math, and these boxes at the top are people taking English. So it's all three of those boxes are taking math or they're taking English. So we just add those up, don't we? Because or always means add. So 52% plus 25% plus 20%. Now on one like this, you could divide by the total if you want, but the total is just 100%. So with percentages, we don't need to divide. It's already percent, huh? So that's going to be 45. 97? 97% chance. 97% chance that they're taking math or they're taking English. We good there? Is that making sense on that? All is well. Now they ask another question. Find the probability, blah, 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 taking neither math nor English. What's the chance they're taking neither math nor English?
3%.
Yeah, that's just right there, huh? Because that's the no for both. Is that making good sense? So you good with making those tables? And the questions come not too bad. Questions on that one?
Will the tables always look like that, or sometimes will they look different? Like if it was like 3 different kinds?
Oh, yeah. I think it'll just be a 2x2.
Okay.
Unless I'm forgetting something, William. I think they're just all 2x2s. Okay, what if I have a new game at the casino? What if there's a new game at the casino? And it goes like this. It says you roll a die, where you bet $2, let's say, and you roll a die one time. And if you get if the result is 1 through 4, you get nothing. You get nothing. But if you get a 5, they pay you $3. And if you get a 6, they pay you $6. No, let's make it even higher. Let's make it $9. All right, $8. Sorry, I keep changing my mind. Let's see if I got that right. Yeah. So what do you think? Or even 9? Yeah, I keep it. Back to 9 again. One more time. Even 10? Wait. 10, all right? Sorry, just 1 second. I'm thinking it all out. All right. Anyway, let's just try it that way. I can't do it in my head. Anyway, would that be a good game to play?
No. Not for $2.
Yeah, not for $2. Yeah. Yeah, for a $2 charge, would that be a good game to play?
Statistically, are you down?
Nobody has a die in them. I bought a pack of 100. I'm going to bring my dice to class in a week or two. I want to actually do a couple of these things. I like this because I think it's very interesting. So, and we'll do a couple of quick, like roll the die, try stuff out. Yeah, in fact, I'll probably bring it on Monday. So I'm giving you the theory right now. I could roll a 6, and then I win $10.
It would be a good game to play.
Would it be a good game to play?
Because if you roll it 6 times, you'll pay $12, but you'll make 13. What? Probability-wise, right?
Good thinking, William. I like the way you think, man.
But you only roll it 1 time. It says $2.
Well, you want to explain? Tammy says, but you only roll it 1 time.
Well, okay, so
It's $2 a roll.
yeah, and why don't you
Listen to William, he's got it.
Teacher, man.
No, I like what you said. All right, I'll expand on what you said. William knows that, and he's thinking the right way. He's thinking, well, just imagine what's going to happen if you roll to 1, roll to 2, roll to 3, roll to 4, roll to 5, and roll to 6. Because probabilistically speaking, that's generally what's going to happen. Now, not perfectly, not every time, but in the long run, which is always what we're interested in, right? In the long run, we're going to eventually roll all the numbers, right?
It's just one die.
Just one die. But we're going to roll it tons and tons and tons and tons of times. So we're going to cycle through the numbers 1 through 6.
But is it $2 a roll?
$2 a roll.
So 2 times 6 is 12.
So when we roll a 1, what's going to happen?
What if you 6 times you get
When we roll a 1, what's going to happen financially? Lose $2. When we roll a 2, what's going to happen to our bank account? Lose $2. When we just the $2 we paid, and we don't get anything back. When we roll a 3, what's going to happen to our bank account? Same thing. Roll a 4, what's going to happen to our bank account? Same thing. Now, when we roll a 5, what's going to be the net effect to our bank account?
$1.
Gain $1. Only one. Because we paid 2 to play, and we got 3 back. Right? And if we roll a 6, what's going to be the gain? $8. Right? Because we paid 2 to play, but they pay us back 10. So this is another way. You did it with the whole 12, but I'm just doing the same thing. Another way to say it. So, this is a minus, hit the button there, minus 2, because they're losses, right? This is a gain of 1, gain of 8. Add all those up, you know what you get? Positive 1. Meaning, you can expect to win on average with this game. That's what William was pointing out. Do you see, if you did the whole cycle, you would win more than you lost.
If you got that.
Well, that's what's going to happen in the long run. That calculation we just did is what I want to show you how to do. I'll write it out step by step more formally. That is the calculation the casino lives and dies by, and live they do, because they do it right, and they know they're going to win every game in the long run. That calculation, I'm going to bring you an article too. I found this great article put out by UNLV, University of Nevada at Las Vegas. That university did a big study on all the probabilities. It was really great. I was reading it the other day. So let's calculate. They would not offer this game, this means, because they would lose at this game in the long run. When this comes out positive, that means you're a winner on average in the long run. Let me show you. So it's called an expected value calculation. Expected value. So here's how you do it. Expected value. So we'll just go through one of these, and that's all we'll have. And then we'll do a bunch more next time. So expected value calculation, what you basically do is you put the net dollars. In fact, let me go to a fresh screen. So for expected value, this is how the casinos know, or anybody, any game, you can figure out what's going to happen in the long run on average. You have in one column the net gain, the dollar net gain, and in the other column you have the probability of that happening. So we come back over here, and we have all these results, right? So if we roll a 1 or a 2, well, let me make it a little more simply. If we roll 1 through 4, any of those, we're going to lose $2, aren't we? If we roll 1, 2, 3, or 4, we're going to lose $2. So we're going to lose $2 negative to our bank account. If you roll 1 through 4, you're going to lose $2. And what's the probability that we're going to roll 1, 2, 3, or 4? If I'm going to roll a die, what's the chance I'm going to get 1, 2, 3, or 4?
4 out of 6.
4 out of 6, right? Because there's 6 different things that can happen, and that's 4 of them. Are we good so far? Is that making sense? 4 out of 6. Next column, we could roll a 5. If we roll a 5, what's going to happen to our bank account? Remember how the game works? They pay you $3. And you paid 2 to play the game. So what's the net effect to your bank account? You made $1. Positive $1 to your bank. So notice I'm always doing net. like final effect on your bank account. I did not put the plus 3, did I? Because that's just what they gave you back. I did the 3 minus 2, the net effect to your bank account. So it's net. So, and what's the chance that you're going to roll a 5? 1 out of 6, because that's one number out of 6, huh? And finally, if you roll a 6, they'll pay you $10. So if you roll a 6, what's the net gain to your bank account? They're going to pay you 10, but you paid 2 to play the game. So you made $8. And what's the chance you're going to roll a 6? 1 out of 6. So you just lay out the gains monetarily. You lay out the probabilities. I'll show you by hand, but really we just like do it on our calculator. You basically just put these in L1, put these in L2, hit the buttons, and find X bar, like we did a week ago. And I'll tell you what the calculator is doing if you're interested. It's just multiplying these. That's all you have to do. It's just taking the money times the probability, getting an answer, getting an answer, getting an answer, and then adding them all up for us. That's what it's doing. We'll just let the calculator do it, though. So you know what I mean by that? Just take your calculator out, put these numbers down L1, put these, just type them in just like that. Just go 4 divided by 6, enter. 1 divided by 6, enter. Put those down L2, and then when you're done, you hit Stat, and go over to Calc, and one variable, and do the L1, comma L2. Remember the L1, L2 thing that we did before when you have 2 columns, information for 2 columns? Put in L1, L2. Remember how to get the L1? You got to hit second and 1 to get that L1. Let me write that for you. Second and 1. Second and 2. And it'll do it automatically. I'm going to divide. Just literally type 4 divided by 6. Enter. For that one. All right, so here's what I got. When I did it, I got an X bar, which is an average. That's what you're figuring out here. What's the average winnings of this game? I got 0.1666. 6 is forever. Y'all getting that? 0.16666 forever. 7 at the end, but it just rounded the last 6 is all it did. Is that good? Is that coming out? That's the answer. That is the expected value. What does that mean? That means on average, you're going to make 16, well, I guess around to 17 cents every time you play this game. You think, well, you can't make 17 cents. There's no way to make 17 cents. Right, that's the average. You won't do that in any one roll, but that'll be the average. So after you've played 100 times, you'll be positive $17. Very close. This is what I want to do with you next time, is have you actually roll it. What's fun to see is that this is the truth. To see that this theory really happens. Then you might think, no, you can get lucky. You can have 10 times. But I'll have all of us do it, and then put the day, like everybody do it 10 times, and then we'll have like 500, all together as a class, and you'll see the law of large numbers takes over, and the average winnings will come out super close. It's like we're each winning 17 cents per roll on average. It'll end up, it's amazing how much reality follows theory when you have a large numbers, when you don't just do it. If you just do it 5 times, 10 times, even 100 times, you might get a weird result. But if you do it 1,000 times, you'll see the law of large numbers start to take over, and it'll be super close. Is this coming out okay in the calculator? That's what expected value is. That's the average winnings per roll. It's like every time you roll that die, you're going to make 17 cents. Now, notice that's a positive number, isn't it? Guess what it's called the expected, it's right here. The expected value. Guess what all the expected values are for the games at the casino. I was just at Las Vegas last weekend, right? Guess what every one of them is. They're all negative. In fact, this article from UNLV listed them out. Showed the exact negative expected value. This article I'll show you. That shows exactly. So that's what I mean. It's a science for them. They know every time the die is rolled, on average, they're making a certain amount of money. Every time the cards are played, they know exactly what they're making. It's like clockwork. They just know it. So they even have, interesting, the article showed, they know what a player is worth based on how fast he or she is playing and the average bet. They'll look at somebody and they'll go, that person's betting $10 a hand, 5 hands an hour, playing blackjack. We know that we win with an expected value of 2% times this many hands per hour times this much bet. That person's going to give us about $100 an hour. They know exactly what's going to happen. It is a science. There's actually been a couple of famous cases. The article also had a couple of famous cases where the casino offered special deals and the math people miscalculated, and the games actually did end up with a positive expected value, and gamblers took thousands of dollars from the casino like over the weekend, and then they went, oh yeah, no, change that deal. Then they realized that they did the math bad. There's a couple famous cases where they did the math bad. They have math people. This is all mathematical for them. They know exactly, well, then they mess up every now and then, a few especially. And when they mess up, they lose money fast because then it's in the gambler's favor. It's a positive, and they offered a couple, so I'll show you the article anyway. So that is the calculation that, and it's going to be the same thing. We'll do it for insurance policies as well. It's exactly what an insurance company does. When they set policies for you having a car accident or life insurance or fire insurance on your house, they're calculating, that's gambling in a sense, right? The probability that you're going to have a car accident and what you pay to play the game, called your insurance payment every month, right? And what they're going to pay out if you win, if you crash, I guess that's you win, right? What they're going to pay out. They calculate this exact same thing. This is how they know where to set their policies and what's going to happen on average to make sure they're going to make money and how much money they're going to make on average per policy. That's exactly what they do. It's this calculation. There's a whole area of mathematicians called actuaries. That's their whole job. They sit around and they calculate these expected values. All right. So we